The ice sheets of Greenland and Antarctica are millions of years old and kilometers thick. But have you ever wondered, what lies beneath all that ice? Thanks to a groundbreaking dataset from NOAA's National Centres for Environmental Information, we can now map and understand the landscape beneath. The eTopo 2022 dataset combines airborne LiDAR, satellite-derived topography, and shipborne bathymetry data. And the data are completely free and open for anyone to access and explore. In this video, I'll guide you how you can use Python to access and plot the bedrock bathymetry and ice surface bathymetry data. I'll also show you how you can quickly compute the thickness of the ice from this dataset. In doing so, you'll learn how to read and plot data from NetCDF files, how to stream data directly over the internet using OPeNDAP so that you don't need to download large files to your computer first, how to write the data into a 2D NumPy array, or alternatively into a Pandas Dataframe that you can save as a CSV or Excel file. And finally, you'll learn how to loop through multiple files and combine the data. If you use these data, please make sure that you cite them as it states here. The data have been assigned a CC0 license, and that means that you can use the data however you like without constraints. You can access and read about the data on this page, and I've put a link to this in the description of this video, along with the code and everything else that I'll refer to today. So let's get started. The data are available in either GeoTIFF format or in NetCDF. We're going to use the NetCDF files. There are three separate datasets within this collection. We have the bedrock elevation, the ice surface elevation, and the height of the geoid. So let's start with the bedrock elevation, and this has taken us to a THREDDS data server. We can see that the data have been broken down into a number of different files, and we can think of each file as a 15 degree by 15 degree tile. Breaking down really large datasets into smaller files is generally considered good practice because it allows people to access just the data they're interested in without having to download each individual file. So let's start by clicking on one of these files, and we're going to access the data using OPeNDAP. OPeNDAP allows you to stream data over the internet without having to download the data first. You can just copy and paste this data URL into your Python script and use it just like you would a local file path on your computer. So let's open up Python and load these data in. Let's start by importing Xarray as XR, which is going to help us load in our NetCDF files. And we'll call this dataset ds equals xr.open_dataset, and we can paste into here our URL. And then let's have a look at the dataset. So we can do print ds, and if we expand our terminal below, we can see the data here. The data are two-dimensional, having latitude and longitude as coordinate variables, and we have a data variable for the bathymetry z here. Let's get rid of this print statement and we'll access the data. So if we want to access the latitude variable, we can do that using ds and in square brackets the name of the variable we want to access, which is lat. And if we print this out below, we can have a look at it in our terminal. We can see that we accessed a Xarray data array. And this includes all the variable attributes, which are the metadata that describe the latitude variable. If we want just the data values, we can access them by doing .values, and we'll run this again. And the data are plotted here as a one-dimensional NumPy array. If we instead want to access the bathymetry, we can call that z perhaps, ds, and the name of the variable is z, and .values here. And let's print that. We can see that the bathymetry data are stored in a two-dimensional NumPy array. Let's say we want to write those data to a Pandas Dataframe. We're going to simplify this script a little bit. We can do this, and we'll say df for our data frame is equal to ds, z, the name of our variable we want to access, to data frame. And we'll just print the head of our data frame below. And we can see that our data frame includes not only the bathymetry data, but also the latitude and longitude data. Let's say we want to write these data to a CSV file instead of printing them. We can do that by just going df.toCSV and say, call it something here, bathymetry data.csv, for example. And we'll run that. And we can see the CSV file here. So now let's go to plot the data. We can remove these lines. Let's say bathymetry equals ds z. And we can do bathymetry.plot. And then to present that plot, we need to use a different library. Import matplotlib.pyplot as plt. Then we just do plt.show. And it should be as simple as that. And there we go. We will improve upon this plot, but firstly, this did take quite a while to plot. Unbeknown to you, thanks to the magic of editing. These data are quite high resolution, and we certainly don't need the data to such a high resolution in order to plot them, at least not for the sake of this tutorial. So what we can do is resample our data, or perhaps downsample our data, to select every 10th value of longitude and every 10th value of latitude. So then there are 100 times less points to plot. So how do we do that? Well, we can go up here. We can assign a sampling factor of 10. And then we can do ds pre-sampled is equal to ds.iCell, which is selecting data based on the indexes. So if we start a new line, we can select based on latitude, and we're going to use a slice. So the first two values here are going to be the range from the start to the end that we want to select based on. So if we wanted to select based on the 0th and 10th index, we would do this. But in our case, we want to select the entire data range, so we do none and none, but only every 10th value. So we can do this here. We can do the same for longitude. In fact, I'm just going to copy and paste this. And then we can make our bathymetry equal to this ds resampled and plot this. And that plotted in a fraction of the time and looks okay, at least for the purpose of this tutorial. You can obviously play with this sampling factor based on your needs. We're now going to try and plot these data to a different projection. Now, we can need to use a different library for this. So import cartopy.crs as ccrs. Then I'll assign this at the top where we're defining parameters. And we can do projection equals, for example, ccrs that we've loaded here. Then our name of our projection. So this could be Mercator, for example. There's a number of different projections that you can select from the Cartopy projection list. This page is linked to the description. And you can go down and find which one you're looking for. And there's some information about what arguments you can also assign. We then need to define a figure and an axis. And we basically need to assign that projection to that axis. So we can use plt.subplots subplot kw equals projection and projection. This is a dictionary. And whilst we're at it, let's assign a size for our figure, which we can do fig size equals, in round brackets, maybe 6 by 8. We're then going to update this plot. I'm going to plot this to IM. It'll become clear why we do this later. And we need to use a transform here. So the transform is basically the projection that's used currently to define the data. So we're going to define this here as transform because we're going to use this in a few different cases. And we'll add it here. Transform equals CCRS dot plate carry. And I hope that should be okay. And there we are. Let's improve this figure now. I want to use a different color map. And we can do this using a different library. We're going to import CM Ocean. And CM Ocean is a library that includes a number of different color maps that are useful for oceanography. So in this case, what we're going to use is this topo color map. We increase the size of this screen here, which can be used to plot the topography both below sea level in this half of the color map and above sea level. Let's define our color map here. CMap equals CM Ocean dot CM dot topo. We might also want to define a range for that color map. If we don't, it'll be defined automatically, but perhaps we want to choose. So we can do vmin equals 3000, for example, and vmax equals 3000. So from minus 3000 to 3000. And then if we update our image, I'm going to do this on a new line to make it a bit easier to read. We can do CMap is equal to this CMap variable we defined up here. Vmin is equal to Vmin. And Vmax is equal to Vmax. Remember your commas. If I plot that now, we can see the data here. And interestingly, we're also starting to see this inland area, which is actually below sea level. Now maybe we want to add some contours to our plot. And let's say I want to add contours at an interval of every 500 meters. So if I go down here to where we're actually going to plot these, we need to define the levels, so contour levels. And this is going to be an array for the elevation of each of the different contours. And that can be equal to NP for NumPy, which reminds me we haven't imported NumPy yet. Import NumPy as NP. So these contour levels are going to be equal to our range. And this is going to extend from Vmin to Vmax with an interval defined by this contour interval up here. Now to plot those contours, we can do bathymetry dot plot dot contour levels defined by the contour levels. We need to define which axis we want to plot the contours to and the transform that we want to use. We can define what color we want our contours to be. So colors equals black. And we can define the line widths. So we do line widths with an S equals 0.5. So let's have a look at this. And there we are. What I now want to add is some grid lines for the latitude and longitude. So let's do that. We can do GL equals ax dot grid lines. We need to add the transform, but this time the argument is called CRS equals transform. Draw labels equals true. I'm going to define a line width, so this time line width just singular, 0.5. Color, I want that to be maybe grey. Line style, let's have a dashed line in this case. 2 dashes, a single dash would be a solid line. And if we want to define the transparency of those lines, we can do alpha equals, and I'm going to use a value of 0.7. That ranges between 0 and 1. Let's plot this. It's telling me I forgot a comma. Do that and plot it again, and that's better. Unfortunately, the color bar is overlaying these grid line labels, but what we can do is manually define where we want our color bar to appear and how large we want it to be. So to do that, we need to define an axis for our color bar. So C bar ax is equal to fig.add axes. And here we need to define the left, bottom, width, and height of our axes. So the left, I'm going to use 0.87, the bottom 0.25, 0.03 for the width, and 0.5 for the height. We might need to play with those values later. Then for now, C bar equals fig.colorbar. We defined that this color bar is linking to the image that we defined earlier, this IM here. And the C-ax, the axis for the color bar, is going to be the C bar ax that we have defined up here. We want to set a label for that as well. So C bar dot set label. And let's call that bathymetry and meters. And perhaps we want to set a font size of 12. So we'll see how that looks. We might have to play with these. Well, we can see that our color bar has been added here, but also the default color bar is still plotted here. So what we need to do is go back up to our image, and we can remove the default color bar using add color bar equals false. If we run that again, and there we go. If I extend this a little bit, we can see the label as well. If you don't want to have to extend the figure each time, you can of course just change this in the code. Let's change the width from 6 to, for example, 9. We'll rerun that. And there we go. Next up is to plot the bathymetry of the ice surface. The data are available here, ice surface elevation NetCDF. And the data are divided up into tiles in exactly the same way that they were for the bedrock bathymetry. So we have these 15 by 15 degree tiles. The difference here is that these data span the whole globe. Right from the equator, you can see this N00, E00 here. If we open up one of these, we can access the OPeNDAP data access URL. And this URL is conveniently almost exactly the same as the bedrock bathymetry data URL. The only things we need to change is bed to surface here and bed to surface here. The data are also structured in exactly the same way. We have a one-dimensional latitude array, a one-dimensional longitude array, and Z, our bathymetry, is a two-dimensional array with latitude and longitude as the dimensions. Now, what this means is that if we want to plot the ice surface bathymetry, we can use exactly the same script. The only changes we've got to make is change this here from bed to surface, this from bed to surface, and everything else we can run in exactly the same way. So let's test that. And there it is. The next thing is to compute the thickness of the ice. So I'm going to take this, copy it. This is going to be our ice surface dataset. And this is going to be our bedrock dataset. But we also need to change this part of the URL from surface to bed, and this here from surface to bed. I'm going to move this code up here, and also this code, and all the rest, which is corresponding to the plot, can be commented out for now. So we want to first resample the ice surface bathymetry dataset, then resample the bedrock dataset. So we can do that by just changing the terms in here. And thanks to the magic of editing, that's now done. And to compute the thickness of the ice thickness, you can simply subtract one X-ray object from the other. So in this case, we want to do ice surface bathymetry minus the bedrock bathymetry. And we'll print that to have a look at those values as well. Okay, let's run that. If we expand our terminal, we can see that we have an X-array data array, and our ice thickness values are here. Let's reduce that again. And let's plot those data now. So removing this print statement, we can uncomment all of this. We need to change the label to ice thickness. Instead of plotting with bathymetry, we need to plot the ice thickness. And the same here for the image. And we might want to select a different color map as well. This topography color map was more suited to when you had negative and positive values. Ice thickness should be positive in all cases. Fortunately, CO Motion has a nice color map called ice that we can use for this. We can change the Vmin to 0, and perhaps we want to extend the Vmax to 3500 or something like this. Well, let's try and run this. And there we go, we can see the thickness of the ice and this nice icy cool blue color map. So far in this tutorial, we've only plotted data from one file or one tile. Now let's go ahead and plot the data for all of Greenland. And let's revert back to the bedrock bathymetry data for this. So I've got to do some changes to my script again. We need to change this to topo. This was between -3000 and 3000. This was not the ice thickness, it was the bathymetry. We need to do the same here for the contours and the title. And the code at the top then, we can remove all of this calculation and just make this equal to bathymetry, and that should work just fine. We'll test that just to make sure I've not forgotten anything. That looks fine to me. So we're going to close this down. We actually don't need this line anymore. And for now, we're going to comment out all of the code related to plotting the data again. Because the first thing we need to learn how to do is to loop through and load in data from each of the tiles. So to access the data for all of Greenland, we need to loop through all of the files where they have this N for north in them. We can think of this page as the human interface for the THREDDS server. But if we go to the URL here at the top, we can change this HTML, this catalog.html, to catalog.xml to provide us with what we can think of as the machine interface to the THREDDS server. Now, it doesn't matter if you don't know very much about XML. I'm going to show you the main things here. And taking data from this is not as difficult as it might look at a glance. We have the different services listed here. Each of the different datasets listed here by name. And we have the URL path here for each of the files. This is actually the relative URL path. But if you combine this with the root path for the THREDDS catalog, which is the same for each of these datasets, then you can obtain the OPeNDAP data access URL. I'll show you how to do that. We're going to need a different library to help us with this. So from Cython.catalog, import THREDDS catalog, which has some really useful functionality allowing you to interact with the THREDDS server nice and easily. So what we first need to provide is this catalog URL. And this is just the catalog URL that you saw here at the top of the machine interface. So put this into quotation marks. And then we can do catalog equals TDS catalog, this class here, and the catalog URL. We actually don't need all of this code yet either. So we can do for datasets in catalog.datasets.values and a colon, and for example, print dataset.name. So if we return to the XML file, we can see that each one of these is a dataset, and there's one per tile. And what we're going to do is print this name attribute. So let's run this, and we can see that the dataset name has been printed for each tile. We can also access some different information. If we want to access the OPeNDAP URL, we can do that, equal to dataset dot access URLs, and then in square brackets, OPeNDAP, all capitals. Now we don't actually want to do this for every file. We want to do this only for files in the Northern Hemisphere. So we can do if dataset.name.starts with, and then we can copy into here the first part of the file name, ending with this N for north. And actually, just as a proof of concept here, I'm just going to do this for the first three, where it's N60. So just loading in 3 files firstly, to show you that this is working. We can indent this, and then we can take this line, add it here, and instead of loading from this URL, we can just write OPeNDAP URL in here. And let's print this to make sure everything is working okay. Okay, let's run this now. If we expand the terminal, we can see that 3 different X-ray objects have been printed into the terminal. So how do we go from this to plotting all of the tiles in a single plot? Well, firstly, let's remove this 60. So we're plotting everything in the Northern Hemisphere. We can remove this print statement. And what we need to do is include within this for loop everything that we need to do once per tile. So let's start by uncommenting all of this. We need to use some of this code now. This sampling factor is going to move outside of the for loop because we only need to define this once. So this will go here. The same for any of the code where we're just defining variables. These can go up here. We're going to need to resample every single tile. So this needs to be indented into here. I need to make sure the indentation is correct, like this. We all need to define our figure and axis one time, and that needs to be done before we load in the data. And the figure size I'm going to use this time is going to be 1210. And if we scroll down again, the contour levels only need to be computed once. So this can go here, just after we define the contour interval. But the plotting of the contours and the plotting of the image needs to be done once for every tile. Let's get the indentation right. The grid lines only need to be defined once, and this can be done after the plot, so this can stay here. The color bar only needs to be added once. Probably I'll need to play with these numbers afterwards. And then we only need to show the plot once. So let's remove all of this empty space. What we might also want to select is a different projection. Now, a suitable projection for Greenland might be this North Polar stereo. So I'm going to copy this. But I'm going to set the central longitude to be -45, which will lie approximately in the middle of Greenland. So we can change this here and do central longitude equals -45. So if we run that, and this will take some time, the plot looks like this, which isn't great, obviously. What we need to do is define a box around Greenland that we want to plot, and that'll help us get a nice plot using this projection. So let's define our range at the top. We can do lat min equals 58, lat max equals 85, lon min equals minus 80, and lon max equals minus 10. And then moving down, it might be that not all tiles actually have data within this range, so we can account for that. We can do another selection here. So I'm going to go bedrock ds pre-sampled equals bedrock ds resampled dot cell. So previously we used iCell, but cell allows you to select based on the coordinate values. And we can do lat equals slice lat min, lat max. So select only the data within this latitude range. And lon equals slice lon min, lon max. So now if this object doesn't have any data in it anymore, i.e. if this tile has no data within this range, we want to skip this tile, not plot it, and move on to the next loop. So if bedrock ds resampled and z dot size equals 0, so if there is no data, and that should be two equal symbols, we can print no data in tile, then maybe comma, dataset dot name. And then we want to do continue. One final thing we want to do at the end, after we've plotted this, is to set an extent for our axis. So we can do ax.set extent. Then in round brackets, we can provide the extent as a list, lon min, lon max, lat min, lat max, and CRS equals transform. Before we run this again, if you're someone who likes to track the progress as this is running, you can add a print statement in here. Print dataset.name, so you can see how far you are along. Let's run this now. And there we go, that's not too bad. I just want to adjust the color bar a little bit. I'll increase the size of the figure a little. I'll just adjust this slightly to maybe 9:1. And if I run this again, and there we go. I think that looks pretty good. We only need to make a few small tweaks to plot the data for Antarctica instead. So let's go and do that. So firstly, we want to change the projection. The North Pole stereo isn't going to be any good for Antarctica, so we can use the South Polar stereo. We'll use the same color map and range, but our geospatial range is going to be very different. So we can plot from minus 90 at the South Pole to, let's say, minus 57. And we want to plot the full longitude range in this case. So from minus 180 to positive 180. And then we need to filter, but this time only using the data in the southern hemisphere. The data are likely to be approximately as wide as they are high, but we need a bit of extra space on the side of the color axis, so let's go perhaps 14 by 12 and see how that goes. And I think everything else should be okay. So let's run that now. This will take some time. There are 46 files to read in this time. And there we go. All the code for plotting this, explanations, and some extra tips and tricks are all linked in the description below. If you found this video useful, please hit the like button. I'll be doing a lot of videos in the future on different interesting datasets and how you can access and use them. So if you don't want to miss them, hit the subscribe button. I'll see you next time.